We left off on Monday, because today's Wednesday, talking about this idea of amides, and the idea that amides are really a target. You can get amides from nature, but they're typically a goal. They're somewhere you're trying to get to using the other materials. So in recitation, we've been talking about, sort of thinking about acid chlorides and anhydrides as being materials that are used to get elsewhere. So esters, amides, they're usually the targets. Anhydrides, chlorides, they are the mechanism to get there. They are the tool to be able to get there. Well, it turns out that quite often you still have to manipulate esters and manipulate amides. So we have spent some time talking about hydrolysis of esters, we talked about acid catalyzed, and we talked about saponification, in which we use a base. They are ways of going from a carboxylate ester to a carboxylic acid. And sometimes that's important because maybe in nature you can isolate the ester, but you don't have the carboxylic acid and you want it. Well, what we'll do today is wrap up 21, and then we'll move into 22, which is by far my favorite chapter in the entire two-semester sequence. Okay? Chapter 22 is immense. So we'll tidy this stuff up. In recitation, we'll spend some time organizing ourselves, as we have done this week. And at the end of the day, I hope that people are able to differentiate between chapter 20 and chapter 21. If you leave this until the last minute, which is next week, no, in fact, tomorrow, don't leave it beyond today, you will be lost. And this next exam will be an absolute disaster, which we do not want at this stage. So keeping a track of these things and thinking about some of the ideas that we've dealt with. Acid, what are you going to do with an acid? You're going to protonate something, I would hope, by this stage. And if you have a base or a nucleophile, it's going to switch roles and it's going to attack something. And you'll see that again today. So again, organization is key here. Keep up with this stuff, or else it gets overwhelming as we head into 22 and 23. There isn't an awful lot of new chemistry to come. There are a huge number of reactions, but they're all related to things you've seen: nucleophilic addition, nucleophilic acyl substitution, oxidation reduction, stuff like that. It's now a matter of stamina, keeping up with it, and being on top of things. So this is the slide I'll start with today, this idea of reduction. And you can see now, again, going between different families. At the top, I have the reduction of an amide, which happens to react with LAH, the powerful reducing agent, and it ends up with an amine, and particularly it ends up with a primary amine. At the bottom, as we did previously, if you take an ester, which obviously is related to an amide, and you do the same type of reduction, in this case you get a primary alcohol. So that's consistent, but you'll see now the mechanism is slightly different. I realized I didn't have this mechanism on my slide, so I borrowed one from the Michigan State website, and I'll show you where to go find it. So again, we're thinking about the stability of these molecules. These are both fairly stable systems, the ester and the amide being the more stable of the two. But sometimes we want to get rid of that carbonyl. Sometimes in our synthesis, we've coupled two pieces together through the amide linkage, but we don't want the carbonyl, we want to get rid of it. So we can use LAH, and then we can quench, and we end up with a primary amine. So what I want to sort of emphasize today is that there is a difference here in the mechanisms. There's a slight difference. Because at the top, it looks like the leaving group, we've identified this as R C double bond O X, in this case X is NH2. In all the reactions we've done so far, that X group has left. This is one example where it doesn't. Okay, a little bit different. It's going to be logical in a sense in a second, but really it's a little bit different, because in this case we lose the oxygen, we don't lose the NH2. Down here we lost the O-methyl group, we didn't lose the carbonyl, so there is a switch. Asterisk, smiley face, whatever you use to make sure that you recognize this is something different. Put it on there. Well, I have a mechanism for the top one. We've already done the bottom one, where we kick in 2 electrons and we kick out the O-methyl group, and then we end up with in this case an aldehyde, then reduce that. So I borrowed this from Michigan State, and I hope it shows up. It's not great, but I think it will be okay to work it through. Again, this is from the Michigan State virtual textbook. All I did to get this and find this was to type into Google amide reduction, right? Amide reduction. And it's a nice slide because it's got both of these things on it, and you can compare the two. So amide reduction in Google is going to give you that slide from the Michigan State website. At the top, we have the carboxylate ester being reduced. In this case, we attacked the carbonyl electrophile with the hydride, and we got the tetrahedral intermediate, and everything is negative because we're in basic medium, and then we collapse this tetrahedral intermediate, and that gives us the aldehyde. And everybody knows now that aldehydes are more reactive than esters, so this should go again, and we get a second addition of hydride to give a primary alkoxide, which then gets protonated to give a primary alcohol. That's something we've done several times now. The difference at the bottom is at this step. Okay? We add the hydride in the same way that we have done for the ester. But when we get to the tetrahedral intermediate, we have a choice of which to lose. Do we lose the O or do we lose the N? Now in this case, it seems like we lose the O instead. The oxygen comes off. The oxygen is coordinated to the Al as a Lewis acid, Lewis base interaction. And it now turns out the nitrogen's more nucleophilic, and it kind of pushes out the oxygen. The oxygen now is the leaving group, so it has changed roles. The X group isn't coming off now, it's actually the carbonyl oxygen that's coming off. And you think about this, O is more electronegative, it probably handle that charge a bit better, so it can break off and behave as a leaving group. And that gives you a little bit of a different species. It's completely analogous to the one above it. It looks like an aldehyde, but it's the nitrogen equivalent. And if you understood imines, imines are the nitrogen equivalent of aldehydes and ketones. So it makes sense. We end up with this iminium ion, and then we get a second reduction to get to the primary nitride type species, which then gets protonated in a quench step, and you end up with a primary amine. So I would argue that's a very similar mechanism to what we've done with a slight twist. So make sure you recognize the twist. To us as chemists, it's really useful because we are left with the linkage. You think about what we started with. The amide came together, two pieces, an amine and acid chloride. You link two big pieces together. And then instead of going backwards and detaching them, you can just get rid of the carbonyl, and you're left with a very strong amine type system in which two pieces are joined together. We'll deal with that a bit more in recitation. So that's the answer. Okay? The switch of the leaving group in terms of what comes off is simply based on what's the better leaving group, and you get a slight difference in the outcome. Well, I think in recitation, and I hope this will carry on this afternoon, we've been sort of trying to do very different things, but trying to bring them together as unified sort of ideas. If you have acid, you protonate something, right? And the whole point of protonation is to make that thing more reactive. If you have base, you go after something and attack it. The base is aggressive and it does the attacking. Those are general things. So when we start seeing things we haven't really dealt with before, we should be able to make some sort of a sensible opinion now, or have an opinion about what's going to happen. So I have a system here in which at the top I'm trying to make a nitrile. A nitrile is the sort of odd one out in that it doesn't have a carbonyl. All the other acid derivatives we've dealt with so far have a carbonyl. This one does not. But if you look at the oxidation state, if I start down here with the amide, what is the oxidation state of this carbon right here? +3, good. And what is the oxidation state of this carbon right here? It's also +3. They're at the same oxidation state, that's why we categorize them as being the same type of system. And to a chemist, this is a carbonyl. Okay? That's just a simple carbonyl that would be able to protonate and attack and do all sorts of different things, lose systems, lose molecules from it, and it'll do very similar chemistry. So really at the end of this chapter, I have to talk about nitriles, I'll talk a little bit about synthesis and how to use these things, and then we're into 22. And 22 is really the sort of big chapter here. So what mechanism is this? What's happening in that first reaction to make that nitrile? That's an SN2. Any good solvents for this? Any suggestions? DMF, DMSO, THF, things like that, polar A protics that help the SN2 process. And in that case, you've added one extra carbon and a nitrogen, and it's a very good way of making carboxylic acid eventually, and also making a carboxamide eventually. We'll see when we hydrolyze these things. So at the bottom, I have a slightly different system. I have an amide, and it has to be this type of amide, which has two hydrogens attached. And you treat it with SOCl2, which we've seen before. SOCl2 is used to take a carboxylic acid to an acid chloride. And that gives us, again, SO2 as the leaving group, or as the byproduct, and that gets lost, and also 2HCl. So what is being lost here? What is the difference between that molecule on the left and the nitrile? Water. Absolutely essential that you see this. So it's a dehydration process. It does not involve any oxidation reduction. That's why you can say they're both related. But it is certainly involving the dehydration of something. So we're going to lose a molecule of water here to be able to get to that product. So if we look at how this works, at the bottom I have the amide. And you could argue now that the amine part of the amide is quite nucleophilic, or it pushes its electrons into the carbonyl. And that makes the oxygen here fairly nucleophilic, which is why it goes after the sulfur in SOCl2. And after we lose this chloride, what's this species called up here? What do we call this thing? Tetrahedral intermediate. You're seeing the consistencies now. There are only two mechanisms left. They just have lots of different varieties. Tetrahedral intermediate collapses with loss of the leaving group, and we're left with this species. And all we have to do now is think about, all right, I have too many protons here. I'm trying to get rid of those protons, so let's take one off as an acid with a base, and then I have that second proton to get rid of. At the end of this, what does this mechanism remind you of? You have a base coming in, taking off a proton. At the same time, a pi bond is forming, and the leaving group is breaking off. What is that? That's an E2, all day. So it's, again, yes, there are more atoms. Yes, it's more complicated. Yes, it's a different flavor compared to a simple E2 that we saw last year, but it certainly looks like an E2. If you're getting this stuff, it's starting to come together. You can start to predict things. Michael? In this case, it's something like pyridine. Yeah, you run this with something weak like pyridine. And that's a good question because you don't need a strong base because you're not taking protons off at the beginning. You're mopping them up as we go. I've been using this phrase, mopping up protons. Pyridine's very good at that. After the fact, you think about the pK of these protons in these species, it'll be quite low because the nitrogen is positive. and you don't need a super powerful base to do that. So something like pyridine or triethylamine would work quite well. So now we have two entries into nitriles, either direct introduction through SN2 chemistry or dehydration of a carboxamide. Pierce? Yes. So in this case, it's because it's not my slide, but because you've lost HCl here, one of them goes there, and you've lost the other one there, and the two hydrogens have been picked up by the base. So maybe to make that slide a bit better, you might put that in quotes. It's the equivalent of 2HCl. That makes sense. I think it balances out that way. So again, people will start thinking, wow, this is a huge amount of material. And the whole goal here is to recognize that it is, but it isn't. The fact that if you understand some of these things, you should be able to tackle these things just because you know how to do this. So in terms of other things we can do with nitriles, they are very useful materials. I have a couple of reactions to finish off here. They are useful because they're so simple to make by SN2 chemistry. And you think about it, it's like a carboxylic acid piece. It's like a small piece that you brought in by a very simple SN2 reaction, which then can be sort of unveiled or revealed as a carboxylic acid if you hydrolyze. So in this system, which we will do in recitation again, we have the nitrile, we have acid, and we're heating things up, and we're going to end up with a carboxamide. And if we're careful, and we can stop that, we can end up with the amide. If we go further, and we heat it for longer, we can end up with the carboxylic acid. Again, new mechanism, apparently. No, it's not. It's very similar to what we've seen. So if we have a proton, what are we going to do? Oh, I hope you people protonate things next week. That would be really nice. I'd be really happy. Where's the lone pair to protonate? On the nitrogen. So that first step of this hydrolysis process is doing exactly what we've done for a while now, which is protonate a carbonyl, except this happens to be a triply bonded end. Protonate that thing. What does this remind you of? What is the whole point of protonating that thing? Making it more reactive, absolutely. Made it more reactive. And if I were you, I'd sort of draw maybe a resonance structure here to show that the carbon is the one that's losing out here because it's the one that's going to have some delta positive charge because N wants its lone pair back because N is more electronegative. So that resonance structure there needs to be in there. It's important. So what we do then is trap. I have a weak nucleophile, but if you have a strong enough electrophile, you can trap it quite easily with the nucleophile, and we end up here. So far, we can see now that we have something that's starting to look like an amide. We have a double bond N, and we have a single bonded O, simply by adding water to a triple bond. Go back to the alkyne chemistry last year. Triple bond plus acid plus water eventually gave you a ketone, or an aldehyde, depending upon how you set it up. In this example, we've got a double bond and a single bond, ultimately swapping places. That's the only difference between these structures, really. So what is that mechanism? What is that process? It is tautomerism. And if you don't understand tautomerism, ask immediately, or else next week will be impossible. Because there will be products that kind of reveal themselves through tautomerism. And people get stuck. They get halfway there and they get stuck because they don't remember what tautomerism is. And tautomerism will always favor the more stable product. In this case, the amide is the ultimate goal because it's the most stable product for the reasons we dealt with last week. So in this sequence here, we've got a proton transfer to the solvent, and then we've got another proton transfer into nitrogen. In fact, from what I've told you so far, you can go directly from here if you like, just by saying proton transfer, because that's all that's happening. Cut out the sort of trivial bits that we don't need. Well, once we've done that, we've swapped the position of the pi bond and the single bond. We now have the pi bond next to the O and the single bond next to the N, and we lose one proton, we end up with an amide. Everybody in here who wants to pass this class ought to be able to handle that type of stuff. Because it's the same thing again and again and again. So we can take nitriles, and we can turn them into amides, and we can also turn amides into carboxylic acids. This needs to be heated. Any ideas why we need to heat this? Think about stability. Think about the relative stabilities of these things. Amides are quite stable. So you have to push this. You have to force it. But I don't have a mechanism on my slides here for that second step, but I'd like people to have a go at it. What do we think happens first if I have this stuff in there? Oh, I hope so. And we would autoprotonate it here again, I would think. And then if I have water around, what will the water do? It will go after this, and we'll form some tetrahedral intermediate. Then we'll do a proton transfer to the N. Then NH3 will break off, and you're left with a carboxylic acid. I'm not going to spend any time on it because it's the same thing again. You ought to, by now, have some idea in 21 that acid-catalyzed processes are uniform, they're all the same. Base-promoted processes are the opposite. They do the attacking. Karenza? The R to the C to the triple bond O. What did you say? I would give you a clue. That's a fine question for a Wednesday morning. When do you know where to stop? You'll get some clue. Okay, you'll definitely be given some guidance as to where to stop. If you're careful and you know how to do TLC and you can stop this thing and you have some device to be able to identify that you're at the amide stage, you can cut it short and that's it, you isolate that. If you go further and heat it longer and you know how to detect the carboxylic acid, you can go all the way there. Okay, but it is a reaction that requires heat because you're going from something that's quite stable all the way back to a carboxylic acid. So another acid catalyzed process. Leslie? Yes, that's fine. Yes, that's fine. Yeah. In reality, it would be maybe a 10-hour reaction, something like that. I don't know. It would be multiple hour reaction, but it will work that way. Absolutely. Anybody over here? Hello, Cody. How are you? I'm all right. It's Wednesday. It's great. Okay. Moving along. We can also do this with base. And why am I speeding through this stuff? Because it's repetitive. It really is. And if you're in recitation, you're seeing this. We're just practicing this and drilling and making sure that we see that these things are the same again and again and again. Just do sensible things. In this first step, how many protons do I have? None. So don't be protonating anything. That's important. And what's this going to behave as? It has two choices here. We'll say in 22 that it depends on the substrate what this will behave as. But in this molecule, let's say there are no acidic protons around, so what will the hydroxide behave as? A nucleophile, which indeed it does. So in a nitrile, it goes after that carbon of the nitrile, just like that. And if you have to give me a name of a mechanism for that, what is it? You're taking a nucleophile, you're attacking a carbonyl type species, and what's that called? Nucleophilic addition. That looks like a nucleophilic addition step of the first step. Why does it attack carbon and not nitrogen? That's all the way back to the first semester. That carbon is delta positive, that carbon is delta negative. Negative goes after positive. It should. So I'm forming a new bond. And all of a sudden, very quickly, this is starting to look like a carboxylic acid or an amide. It's starting to look like a material like the product. So at the end of this, I've got this nitrogen, which is fairly basic. Don't forget, we're at high pH, so basic things are okay. And this general idea that if you're at high pH, and you can recognize that, your intermediate species will be negative. You're at low pH, your intermediate species will be positive. It's fairly general. So at this stage, we've got a fairly strong base. We have some water around as the acid. No protons like in HCl or H2SO4, but I have water around, which has its appreciable pKa, so we can deprotonate it. And then we get to this. Now, we're about to dive into 22, and we ought to be able to recognize some of these things now. I have a molecule that has a double bond next to an OH. What's the generic name for that? It's a double bond with an OH attached. Enol, right? This is the nitrogen or amide equivalent of an enol. You swap this nitrogen for a carbon, that's an enol. Now, this looks like an enol, it talks like an enol, it quacks like an enol. It pretty much is an enol. So do the same things you would do for an enol. Again, organize yourself like that because you don't have to repeat yourself. So I need to get to the more stable outcome. Why does it do this? Simply because the amide is the best place to be. So I've got this enol form here, if you like. And again, I'm swapping around the proton and the double bond. So what is that process going from this enol to this carbonyl? That's tautomerism. That's all it is tautomerism. Practice tautomerism. It's usually a little part of a mechanism that's kind of, it's placed in there as a final thing maybe to get from less stable to more stable. And it's absolutely essential that you see this because it's showing up a lot now. That's the base-promoted reaction of a nitrile with carboxylic acid. So let's take a second here and just think about this. When you're studying this stuff, a lot of people, you've got physics, you've got mathematics, you've got basket weaving, whatever else you're taking this semester. You've got lots of pressure, lots of things to do. The best thing you can do here with 10 days before this test is get organized now and start to see some patterns, start to see some things that are common so that you give yourself a chance of doing well next week. And again, going back to the very first semester when we talked about mechanism, what do you do to work these things out? Well, you write down that the product of this reaction is a carboxylic acid. You start to identify the pieces. You identify the nitrile as the starting material. You identify the carboxylic acid as the product. That's the very first thing. Once you've got that in your head, at this stage of the game, I would think for people who are doing okay, the mechanism should start to fall into place. The mechanism should start to make sense. We've got a dozen reactions in the past 2 or 3 weeks in which you protonate something first. Very common. Or another half dozen reactions in which we go after the carbonyl with a nucleophile. That's a good start. But you're not going to be able to do a mechanism unless you know the outcome. You need to know what the products are. That's how we work out mechanism. Without the products, we cannot have a chance of working out the mechanism in the lab. So now know the reaction, then understand the mechanism. But when you're writing these things out, keep in mind, where am I going? What do I have to do here? In this reaction, I'm adding overall H2O to a nitrile. So make sure at some point in the game you add H2O. Make sure at some point in the game you add some protons, okay, to make this thing balance. So again, moving along, there's sort of this idea of how to turn a nitrile into a carboxylic acid, and it's no more complicated than where we've been. Now these last few bits and pieces will make make sense quite quickly. What is the pH of this mixture when you mix this stuff with the nitrile? Is it high or low? Don't be guessing at this point. It's very high. It's very basic. So how many protons do I have? None. I've even avoided using protic solvents because they will quench the reagent. So mechanistically, at the bottom, you can see, again, I'm not a big fan of the way that we write this in the book, but RMGBr with the delta negative on the R is good. And then we use the bond electrons from R and Mg to go after the nitrile. What mechanism is that? Nucleophilic addition. That's all it is. And how did you very quickly come up with why it's that way and not protonating anything? Because there aren't any protons. Very simple. So now we add things, and then we've got to worry about the overall process here to get from a nitrile to a ketone. Now, that's powerful. What you've done here is taken what we might call a monovalent piece with one R group attached, and we've ended up with a ketone that has two R groups attached. And when we start thinking about linking things together, there's a very powerful way to do it, knitting these two pieces together. So what does this remind you of? What's this almost? It's on the way to a ketone. But if you protonated that N, what would that be? What type of molecule would that be? Imine, right? This is very close to an imine. So now we're not going to spend a lot of time hydrolyzing an imine because we did that in the last chapter. You can think about protonating this thing and then going to that through a simple hydrolysis. Protonate, attack, proton transfer, lose a leaving group, some resonance, we're done. Now on the web I have an example of this to show you where it's applicable. Just a couple of R groups to confuse things, but it's the same reaction. I have, in this case, something like ethyl magnesium bromide and a polar protic like ether. I'm undergoing a nucleophilic attack on the nitrile like so, with the arrows going in a sensible way to end up on the nitrogen. I then end up with the N- material, which needs a proton, and then I'm done with that process. I'm now on the second step. This is step 1. This is step 2. Step 2 looks like it's pretty complicated, but it's exactly what we did in chapter 20. We're going to protonate this to make the imine first. Then we've got acid, we've got plenty of it. We're going to, and it says here, watch this, quench and hydrolyze. There's a clue. That tells you you're going to go all the way to the ketone at the end. Protonate to make this species. Why do we protonate? To make it more reactive. We can describe that with resonance structures that describe exactly why it's more reactive. It essentially is what we call a heteroatom stabilized carbocation. It's a carbocation next to an O or an N, something that can help with a lone pair. Heteroatom stabilized. So now to hydrolyze this thing, I've got water in here. Everybody, right? If you don't recognize this yet, there's not much hope. What is dilute aqueous HCl? What's in that mixture? Water. H3O plus HCl water. Yeah, so where's the water coming from? It's coming from dilute aqueous HCl. Now, we're going to attack this thing just as we have in the past. What would we call this species here? That's a tetrahedral intermediate, okay? And then I get a proton transfer and I put the proton on the N. What's the point of doing that? Leaving group. Notice in the product, which you know because you learned that straight away, there is no nitrogen, so it must leave. Break it off. Maybe break it off as a positive piece because that's going to be neutral when it breaks off. And that's only allowed if the carbocation's okay. And this carbocation is fine because it's significantly resonance stabilized. If I draw that second resonance structure, we can see now where the ketone comes from. Take off the proton to get the catalyst back, and we are done. That's where we're at. That's something that you shouldn't spend an awful lot of time on because we've seen it before. We're now just putting small pieces together. You can make this as complicated as you want, but it's actually fairly simple if you're taking the time to actually pick this up consistently. Nathan. Now, you can do that. That's fine. That's fine. That's what the book tends to do, right? I'm not against it, but it gives you, and this is what the book does, it then sort of, you forget to write this. Yeah? You forget to write that. And that second resonance structure, we're trying to understand here. If we're just memorizing stuff, I'd just say, forget the resonance structure, just plow your way through. Let's do biology and just memorize it. And then you puke out on my test whatever you know about the subject. No fun. You don't remember it long term. A lot of people in here taking standardized tests in the future, taking biochemistry, taking more organic. You need to remember this stuff. And this helps it sink in. If you keep, hammering away at the basics, it will sink in eventually, whether you want it to or not. So yes, the point was, can you draw this in terms of the arrow, the way the book does it? Yes, you can, but please remember to draw this resonance structure, because that really tells you why this is a stabilized carbocation. So I'm just finishing up now. I have a couple of slides left. These are things that, again, I'm not going to spend a lot of time on mechanisms, because we should be able to handle them from now on. We want to get into 22, so we maximize our time on 22, because it really is very, very, very heavy. So this is a reaction that I don't have a mechanism for, but what do we think is going to happen in the first step? Did you say protonation? Retract that, sir. Not protonation. No. What are you going to do in the first step? Nucleophilic attack, because this material here is a very powerful nucleophile, right? There are no protons around, or else they would be taken up by the hydride and end up with hydrogen gas, and it would probably be dangerous. So away we go. Attack, 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 attack. What mechanism is that? Nucleophilic addition, right? And that gives me a C double bond N, and C double bond N is an imine. And imines get reduced, right? So bring in a second hydride and reduce it, and you end up with a product. It's fairly straightforward. Down at the bottom, compare that with what we did previously. Look at the outcome, the same. Again, why are nitriles considered to be carboxylic acid derivatives? You get the same product. They are definitely part of the same family. So with that in mind, let's have a look at one of these slides. These are great. Wait until you get to biochem. I mean, the engineers like these, right? Because they look like flowcharts. Kinda. Wait until you get to biochemistry, and these things are just ridiculous in terms of how much information's on them. But this is now where we're at. This is what we can do. Functional group interconversions. I've always said that that is one of the two major goals of an organic chemist. And actually in biological chemistry, that's another major goal, is functional group manipulation. Aldehyde to carboxylic acid, primary alcohol to aldehyde, OH group to bromide. Well, look at this from chapters 20 and 21. You can go all over the place now. And you should be looking at that and going, well, if what he said is true, and really this is repetitive, then this isn't that intimidating. If you understand that in most of these reactions, the leaving group leaves. The nucleophile replaces the leaving group. Then the conditions come into play. Is it acidic? Is it basic? And then you can think about mechanisms, how that works. Jessica, 14. That was the diisobutyl aluminium hydride. So you had H right there, you had aluminium right there, and you had a couple of deer antlers sticking off of it. Remember that one? Yeah, only has one hydrogen, so it just introduces one, that's it. So that's where we're at. That's 21. Couple of things at the end. Synthesis. We'll do a lot of this in recitation. There is a ton of stuff out there to practice. You do as much as you can, as much as you want. I've put the homework out for 21. It's due on Saturday night. I think that's just a kick up the backside to make sure that people get on this as soon as they can and not leaving it till next week, because that's way too late. So I'll do the quiz, and that will probably be due on Sunday night, maybe Monday night. But I'm pushing this to get this done. You don't want to be lost in 21, because 22 is about to happen. So in this case, we can do all sorts of different things. At the top, there are some sensible things to do. There are some not so sensible things to do. You can take amides and turn them into acid chlorides. That is not something I would find intuitive as an organic chemist. With 30 odd years of experience on this stuff, that's not something I would really be looking at doing. I bet I can find something to do that in an easier way. I bet I can find a carboxylic acid with this structure and simply turn it into that compound with SOCl2. That's what you look for in a catalogue or online to buy the stuff. This might be important because this might be a natural product that you've found that you can buy in a ton quantity, and you want to get rid of the NH2 and you want to turn it back into the carboxylic acid because the carboxylic acid might be rare. So that's something you might want to consider. Down here, this is very important, obviously, turning the carboxylic acid into the acid chloride. Now, you'll say, well, carboxylic acids themselves react to give useful products. Yes, they do, but their utility is somewhat limited. You're stuck with, for example, acid catalyzed things. Because if you treat a carboxylic acid with a base, it simply deprotonates it. That's not much use to you. So if you turn it into the acid chloride now, this is a surrogate for the carboxylic acid. It's much more useful because there are no acidic protons and you have a really good leaving group. So that's a very, very sensible thing to do. And again, at the bottom, this to me, that's kind of not a sensible thing to do. Point being, Acid chlorides and hydrides are very good entries into esters and amides. In terms of where we need to go now, we're going to expand on this. We're going to start talking about how nature produces carbon-carbon bonds for the most part, and it's going to complement and supplement what we've done here. This is a review from the past. If we take one of our one of our carboxylic acid derivatives and treat it with an excess of a Grignard, and then we quench, we get a tertiary alcohol. We've done that in recitation this week. We'll do it again today just to put it in place. If you want to think about stopping that at the ketone, you need to calm down the reactivity of the organometallic. In this case, we get away with copper. The copper metal bond is such that it isn't super reactive like copper, like carbon magnesium, and you can actually stop at one substitution. And then if you think about what we just did, we can also make ketones by making carbon-carbon bonds with Grignards onto nitriles, and going all the way back to last term, simply by doing an SN2 reaction, you can bring in a carbon-carbon bond, and then from earlier this semester, 13 and 14, when we did Grignard reactions, you can also turn those into carboxylic acids. You can get overwhelmed with this stuff unless you try to keep up and ask some questions if you need to. I've had a few people in my office this week asking how to organize things. I'm quite happy to sit there and help you organize it. It's not that difficult. But if you're just going to sit there and it's all going to get overwhelming, next week will be no fun whatsoever. All right. How do we use this stuff in synthesis? Well, think about the things we've done. Think about what we can use this for now. If you want a tertiary alcohol, start with an ester. Start with an acid chloride. Because it's a very simple one-pot reaction to get there. You add an excess of the Grignard, and it takes it all the way to the tertiary alcohol. You could go from a primary alcohol to an aldehyde, then add a magnesium reagent to give a secondary alcohol, then oxidize it and make a ketone, then add the third reagent, the third Grignard, and then quench that, and you end up with a tertiary alcohol. That's a lot of work. Start with this and get it all done in one go. Just add the two equivalents right there. And so now, I think what we've done is hopefully given you some idea of what those things are useful for. Again, a lot of this is recitation. A lot of this stuff is just practice. Think about the sort of what's happened here. How do we think about joining pieces together? I'm going to jump over this quickly because this is what we're going to do in the next chapter. We'll spend a lot of time on that. At the end of the day, last slide in that chapter, a little bit about the spectroscopy. Don't forget, we've got certain wavelengths in IR for carboxylic acids that ketones don't have. We've got all sorts of possibilities for NMR. And again, with the final coming up, that stuff needs to be reviewed, and you need to be okay with it. So stop me before I press this button, because this is going to be
is that a concerted hydrogen shift in the AL forms a compound with the nitrogen, or is that only something?
That's a Lewis acid, Lewis base interaction. And then you can lose hydride from the AL to balance it out. Yeah, but I can talk about that in more detail afterwards. Is anybody familiar with the phrase crossing the Rubicon? Crossing the Rubicon. It's something that Julius Caesar, it's a river in Italy, and Julius Caesar was fighting an army, a battle. And he had a choice of either confronting them or not. And to confront them, he had to cross this river called the Rubicon. And ever since then, it's become this sort of metaphor for no way back. You are fully committed. Now, you already crossed the Rubicon because you're here past the withdrawal date. But if I were to point out a place where things either go really well or go really wrong, it's here. So when I press this button here, the Rubicon has been crossed. Are you ready? I can go backwards and do other stuff. I can stop now completely. Let's go. All right. That is the end of 21. Hello, Andrew.
The last slide you had on there, are those going to be the kinds of clues that you give us?
Oh, yeah. Yeah. Again, think about the context here. I'm not going to bring in 15 different types of new questions for you. I'm going to test you on things with devices I think work, with questions that I think work and make you learn the stuff appropriately. And most important to me, make you remember the stuff. So yes, you're not going to see a whole bunch of new questions, but you will see clues. If I think a carboxylic acid absorbance in the IR is useful, I'll put it in. If I think NMR spectra are useful in terms of clues, yes, definitely, absolutely. So I'm going to move into 22. I wish I had some dramatic music for this, but I don't. 22, to an organic chemist who's interested in biological molecules, interested in pharmaceutical stuff, who's interested in just making bigger systems. This is really, really, really key, really important. If you take biochemistry, you'll do a lot of these reactions again. It won't be quite so nicely detailed and quite so stepwise. It'll all be, okay, this is an aldol reaction, go to it. This is where we build up to that. So I'm going to focus for 15 minutes here before we quit today on a shift, not a hydride shift or a methyl shift, but a move in terms of the possibilities around carbon. What can carbon do? So far we have said that putting a negative charge on carbon is a bad thing. Well, now all of a sudden we will be okay putting a negative charge on carbon. It will need some help. If you have a Grignard, CH3, NGBr, that is forever a unstable reactive molecule. There's nothing else you can do with that. That will go after something, add to it, and it won't break back off. Well, that negative charge on that carbon is unstable because the carbon only has electronegativity of 2.5. It's not a big atom, and it can't spread the charge out. 22 is all about putting negative charge on carbon, and all of a sudden you can spread the charge out. All of a sudden there's something else in this molecule that allows for delocalization, which helps stabilize that carbon versus the earlier Grignard type reagents. And this is all based on something called enols and enolates. Sometimes that, in fact, that is partly the title of the chapter, enols and enolates. And we're going to find out that there's a huge family of organic nucleophiles based on carbon that have charge next to a carbonyl. And the whole reason why these things are allowed and why they're stabilized is the delocalization into the carbonyl. And that will only happen in a certain place. I'll show you the geography in a second of a molecule which is bigger, and we'll decide that only one place here this is allowed. And it ties together very much with the previous two chapters, which is why you need to be on top of that stuff today, or else this gets overwhelming. What we did in chapter 20 was a lot of chemistry where we brought in a nucleophile, could be hydride, could be a Grignard, could be water, something like that, could be hydroxide, and we added to make this tetrahedral product. And if I don't have a leaving group attached there, chances are that's the end of it. Maybe you quench and you end up with a product. But you made, if the nucleophile is a carbon species, you made a carbon-carbon bond. If this was a different molecule with a leaving group attached, that was chapter 21. And if you brought something in, chances are the next thing that happened was the leaving group broke off. And then maybe you did it again, maybe you added it again, depending upon the nature of the reagent. So we're going to spend a lot of time now, in fact, the best part of 2 weeks. I'll get some of it done before the test, I'll get most of it done after the test, heading for the final. It turns out that if you have an aldehyde or a ketone with a proton next to the carbonyl, that proton is said to be enolizable through the process of tautomerism. This is kind of going backwards from where we were. We now have systems in which that proton is not always on that carbon. And we can now see that the moving of the pi bond from between the carbonyl to between two carbons, that's a process we've seen a couple of times. It's tautomerism. And we'll have to be happy with the fact that this can happen in neutral pH, it can happen in base, and it can happen in acid. But again, the systems will be the same. The questions will be the same. If I have a proton available, what should I do? Protonate something. And then things will fall into place. But again, you need to know the outcomes to be able to work out the mechanisms. So I have two definitions here. I have enols, and enols are neutral. Enols are neutral, that's key. So the pH here is not low or high, it's neutral. As opposed to enolates, which are more reactive because they are negative, and those are negative species. So once again, as we put these things together, if I'm making 8 enolates, the 8 is the negative part of it, that's the clue. If you're dealing with enolate chemistry, you're dealing with negative things as the intermediates. And once we've defined those things, we have to recognize that it's only possible in certain places in these molecules. You can't be taking protons off any single carbon. It has to be in a certain place, and that's what this slide is about. This is defining the geography of a carbonyl system beyond where we've been before. Everything we've done so far has been attack at the carbonyl carbon right there. We will do a lot of that. We will do a lot of that. But we can generate new nucleophiles now by recognizing the acidity at what we call the alpha position. And the alpha position is simply the one next to the carbonyl. We'll do it with aldehydes, ketones, we'll do it with esters primarily, and we'll be able to make carbon-carbon bonds by using those species as nucleophiles after we deprotonate. So I now have a system at the bottom. I can see here on this system on this system at the top, I have 2 hydrogens here. I have 2 alpha protons. And going back to some of the earlier stuff, I've got 1, 2, 3, 1, 2, 3, 4. So I've got 2 types of alpha protons. That will become apparent next week. 2 types of alpha protons means you might get chemistry on both sides, which confuses things. but it's only at the alpha positions. Beta, why is beta too far away? Why does beta not work? You cannot delocalize into the double bond. You cannot use the double bond's electron withdrawing ability if you deprotonate at the beta position. Certainly with gamma, way too far away, delta, way too far away. So it's all about now the alpha carbon. That's what 22 is all about, alpha carbon chemistry. So at the bottom, we've got to be careful. We've got to make sure that we recognize that there are some limitations here, that not every aldehyde or ketone will have an alpha proton. That will be useful soon. In this butyraldehyde, we've got 2 alpha protons. Okay? Those might come off. We only ever take one off at one time. Both of them might come off eventually, but we'll take one off at one time. Keep it simple. And down at the bottom, how many types of alpha proton down there? 1. There are no alpha protons here, so that can't be. These are beta protons. There's only 1 type right there. So you'll have to make decisions very quickly in the next week or so about where the deprotonation happens in a molecule that has several different types of proton. So leading into this, leading into the idea of why this is useful and why biology uses it so much, is that enols and enolates are pretty good nucleophiles. We will spend quite a lot of time doing this. We will spend a lot of time going after some electrophile, because a double bond is nucleophilic. You put an OH on a double bond, it's more nucleophilic, because you've got a pair of electrons here, which maybe is helping that process happen. So having the OH group there makes the double bond more nucleophilic than we've seen in the past. And we have added in this mechanism, which isn't shown, but we can think about it. Why does the E group go here and not here? What rule is this? You're adding to a double bond and you're getting one outcome. What's the rule? Markovnikov. We're going all the way back to Markovnikov. And we'll find that if we do this, we're going to build up some positive charge here. And that positive charge is best next to the OH group for the same reasons it was in 20 and 21, because that OH group can help through resonance. So you're going to make, again, resonance stabilized carbocations. Down here, we've got the possibility of doing this with base. What we'd do here is take off that proton, make the enolate, and then it itself is nucleophilic. We can use that again to go after, and you'll be doing these arrows a lot in the next couple of weeks. Do that. Okay? Nucleophilic attack at the alpha carbon. So it is a fantastic way of functionalizing materials at carbon by making carbon-carbon bonds. But at the same time, you have functional groups available. You have a ketone available which is necessary to do this, but then that ketone can be used for something else. Once you've made that carbon-carbon bond, you can then use the ketone to do all sorts of different stuff, as we've seen in a lot of detail. So this is, without scaring anybody, this is going to be a step up. And for those of you who want to go further, like into your junior or senior years, this has to be understood and you have to do well at this. So I'm going to finish this off. I've got a couple of minutes here, and then we'll break. Ketones often exist also as enols. But there are some facts here. A typical ketone prefers to be the ketone. It does not prefer to be the enol. And the answer is simply bond strengths. It turns out that the ketone is more stable than the enol. If you add up the bond energies, the ketone's better by about 30 kcals per mole. So that tells you that in this system, if you took its NMR spectrum, you would see mostly ketone signals. You wouldn't see this signal down at 5 because there's not very much of it in there. So the fact is, ketones prefer to be ketones. Keep a track of that. If you look at some other systems in terms of enol content, it should start to make some sense. If we start off with this diketone, which we'll see a lot of towards the end of the chapter, well, it turns out now that this side is preferred. Any ideas? What do we have going on for this molecule on this side that it's better? Say again? Delocalization. I'm not sure about delocalization so much, or maybe a little bit, yeah. What is the relationship between this carbonyl and this double bond? They're next to each other and they are double bonds. What's that called? Conjugation. It's conjugated. And particularly in this 1,3 example, what is this trying to show you here? Hydrogen bonding, which is also worth some energy, right? It's also some good glue to hold the system together. So those ideas you'll take into biochem. The idea of hydrogen bonding to a system and also maybe conjugation of the system will help stabilize it, even though, yes, these are ketones and this is an enol, but this enol's better because of those factors. Down at the bottom, I have a system in which I have next to none of the keto form, and it almost exclusively is the enol form. Why is that? Aromaticity. So there's nothing different here. It's all stuff we have done. And I will say that there is very little of anything different in 22. It's just more of it and more complicated. So before I leave today, I want to make sure that you're happy with where we are. I am. It's my favorite chapter. Did I say that yet? But it's also the busiest chapter you'll get just before all the exams come up. We're going to see next week, no, because we have class on Friday. We're going to see on Friday the idea that, again, we can understand the use of protons and the use of bases on carbon-based molecules. So in this condition, under these conditions, I have a proton. So what do? First, I protonate something. That's exactly what happens here to give this. And then the next thing I typically draw on those mechanisms is a positive charge to show the resonance stabilized cation. And then to get to an enol, I need to take off a proton. And we've seen this with enamines very recently. We've seen the same thing. What is that last step? What does it remind you of? What reaction does that remind you of? E1, good. And for those of you who get this stuff and it's starting to make sense as a language, that's all it is, adding things together. Michael? So that's a good question, which we'll deal with when we get to the aldol reaction. Hydrates will get formed. And we're about to see mechanisms in which you can go in 4, 5, 6 different ways. But because they're all equilibria, you end up at the best place. And hydrates are typically not the best place. They're not the most stable things. So we'll be doing a lot of this in the next week or so, backwards and forwards, getting to something good. Especially when we get to the aldol, the Robinson annihilation, stuff like that. That's big. Down at the bottom, last thing to say today, we have changed the pH. The pH is now high. It's basic. So now we can have the idea. And the same question here. Why does the hydroxyl not go after the carbonyl? And the answer is it does. It does. It gives you a hydrate. But that's reversible. And if we can now go in this direction and put some negative charge on here, I can stabilize that by delocalization, looking at the enolate, and then I can deprotonate and I get the enol again. And that enol will go someplace else. That's the whole point. The enol is formed to go someplace else as a nucleophile. We'll leave it there. I have some quizzes if you didn't pick them up last week. Get on this stuff as soon as you can.